Hello, my name is Monica and this is Lab 3 Circuits. The purpose of this lab is to use the principles of energy and current conservation to observe the behavior of circuits containing resistors in a series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and finally examine the behavior of ohmic resistors and capacitors. Two graphs are then created based on these results. For the first part of the lab, the current flowing through the series circuit was 0.02 amps, while the experimental RC time constant was calculated to be 5.96 seconds in the RC circuit. Principles used in the first part of the lab include the energy principle or the loop rule, which states that the sum of the series net voltage is equal to 0. The node rule states that the current is equal to the current out, and Ohm's law states that the voltage of a circuit is equal to the current divided by the resistance. For the second part of the lab, a linearization formula is used to calculate the RC time constant. In both circuit setups, the system was the closed circuit, so the batteries, wires, resistors, light bulbs, multimeters, and capacitors, while the surroundings were everything else. An assumption for this lab was that the resistance in the wires was negligible. The initial conditions were set up for the series circuit was two 1.5 volt batteries, 47 and 100 ohms resistors, 2 ammeters, and a voltmeter. For the RC circuit, the setup included a 9 volt battery, a 10, 20, and 30 ohm bulb, and a 200 mF capacitor. For the first part of the lab, the series circuit started out with the batteries, resistors, and 2 ammeters. Both ammeters read 0.02 amps, which was consistent with a prediction calculation using Ohm's law. When one ammeter was connected backwards, the reading changed to negative 0.02 amps. When one ammeter was then replaced by a voltmeter, the ammeter reading did not change, while the voltmeter read 3 volts, which is the total voltage of the circuit. Next, the potential difference was recorded, which resulted in a net voltage of 0, like the loop rule stated. The voltage between the batteries read 3 volts, while the voltage of the 47 and 100 ohm resistors were negative 0.96 and negative 2.04 volts, respectively. The readings were used to create a potential difference versus position graph. As seen, when the voltmeter was attached to the circuit, the ammeter remained 0.02 amps because the voltmeter had a high resistance, causing negligible change in the ammeter reading. Furthermore, when the ammeter was attached parallel to the 100 ohm resistor, its reading changed to 0.06 amps because the current was split. Lastly, the resistance of various circuit elements were calculated by dividing the voltage by the current. For the second part of the lab, the RC circuit started out with the battery, the 10 ohm bulb, and a capacitor. When the circuit was connected, the light bulb quickly lit up brightly, then dimmed out. When the bulb was connected to the capacitor only, again, the light bulb lit up quick, then dimmed out. When the battery was in the circuit, the capacitor was charging, while in the second circuit, the capacitor was discharging. In both circuits, the current would decrease to 0. Next, the time it took for the capacitor to charge and discharge was recorded. For the 10 ohm bulb circuit, it took 9.87 seconds for the capacitor to charge and 10.25 seconds to discharge. For the 20 ohm circuit, it took 21.48 seconds to charge and 22.67 seconds to discharge. For the last part of the lab, a circuit with the battery, capacitor, and a 20 and a 30 ohm light bulb was set up. The capacitor was then discharged while the voltage was recorded for 20 seconds by a voltmeter. A linearization versus time graph was then created based on the data, which is then used to calculate the RC time constant. The theoretical RC constant was calculated by multiplying the 30 ohms in the light bulb and capacity for rods to get 6 seconds. For the experimental RC constant, the slope was equal to negative 1 over the RC, which was then set up to be negative 1 over the slope of the graph, which was negative 0.1679. So the time constant was found to be 5.96 seconds, which is very close to the theoretical time constant. Since our lab's equipment was not working, the lab was made on the Phys simulation. The only possible error could have been in the stopwatch timing. If the capacitor was charged without a resistor in the circuit, the ideal and real-life outcome would be different. In an ideal model, the capacitor would charge immediately due to the assumption that there is no resistance in the circuit. However, in real life, the capacitor would take longer to charge due to the resistance in the wires. Thank you for watching.